Okay, we're going to get started with section 3D. So 3D is going to be about vertical forces. So in the previous units, or the previous sections, we dealt with horizontal forces. Now we're going to be dealing with forces that are in the vertical direction as well. So again, the same tools that you looked at before, we talked about before, the free FBD, so the free body diagram. Like down here, this is an FBD. So this tool where we write all of the forces out, and then Newton's second law, so free body diagrams and using Newton's second law, they can be used to analyze forces in the vertical direction as well. So not just the horizontal, we can now look at the vertical direction. So one thing we got to be careful about is, yes, we can use the free body diagram, yes, we can use Newton's second law, but we need to be careful we're only looking at one dimension at once. So one dimension at once. So that means we can either look at horizontal forces with Newton's second law, we can look at vertical forces, but we got to make sure we do the calculations for each separately. Like if you look at this diagram, there are really three forces here. So again, two of them, and we'll go through what they are, but two of them are in the vertical direction, and one of them is in the horizontal direction. So again, new kind of vertical forces along with the horizontal. So when we're looking, we're going to use some notation to see, so we remember what, if we're dealing with vertical or horizontal forces. So again, remember Newton's second law. Net force is equal to the mass times the acceleration. This symbol right here, we're going to do net force with the little subscript x. This is going to be for horizontal net forces. We're looking at horizontal net forces. Abbreviate that. And then we're going to use sigma F with a little y, and that's going to be the net force, but it's going to be a vertical force, or the vertical forces. So again, we can only analyze one at a time. So there's two forces we're going to look at that mainly act in that vertical direction. Again, the first one is a review. So force of gravity that we talked about in the previous subsection, Fg. Again, force of gravity, F with the subscript G for gravity. That's the force that comes from the planet pulling on the object. It pulls down on the object. Like in this picture, we have this mass sitting on some surface. The force of gravity is actually pulling it down into that planet. The next force, this one's new. It's the normal force. It's abbreviated Fn, so I'll write it up here. F with a subscript n. So this is a normal force. That's the force of a surface on an object. So what does that mean? Let's say we have this box here. The force of gravity is pulling down on it. The normal force is actually coming up from the surface. The surface is pushing up on this box. Again, if there wasn't a normal force from that surface, that mass would just fall through the table basically. But because there's a normal force from the table, there's a balance between that force of gravity and the normal force. So again, we're going to see that a lot. Typically, well, gravity for almost all the time is going to pull down on objects towards the earth, and then, like I said, there's the normal force that's going to be pushing up on that object, keeping it from basically falling through the thing it's on. So that's all the new concepts. So again, vertical forces, we can use the same tools. Notice that now we can have free body diagrams with vertical and horizontal forces. We're going to use notation so we don't get them confused when we're dealing with Newton's second law. And then there are two forces we're going to look at a lot: the gravitational force and the normal force in the vertical direction. So we're going to take a look at a sample problem. Okay, so this is a sample problem. Again, make sure that you take out some time to solve it first before you watch the rest of it and I go through the solution. Again, make sure you're solving it, making sure to solve it, you're not on Twitter or other social media. Okay, hopefully that's enough time. You've given a chance to solve it before you're copying down the solution. So I'll get started. This is an example of a problem that you might see in the future. So what do we have here? We have a VHS tape of Back to the Future, great movie. We know its mass, so it's 100 grams, and it's sitting on a kitchen table. It's saying if you push down on that tape with 8 newtons, what is the normal force acting on the VHS tape? So what is the normal force? We're ultimately looking for what is that normal force coming up from the table. We know some stuff. We know the mass. It's 100 grams or 0.100 kilograms. Again, because the conversion is you're basically dividing by 1,000 because there's 1,000 grams in a kilogram, so you have about 1/10 of a kilogram here. So let's draw out the free body diagram. So there's really 3 forces. There's the VHS tape, surface. So we have the force of gravity pulling down on that tape, right? That's from the planet. That's always there. We actually also have another force. We have not the normal force. We have an applied force. So the applied force is coming from you pushing down on the tape. So again, you're pushing down with your hand on it. So you got the applied force, the force of gravity, and then you're going to have a normal force that actually comes up. So you will have a normal force from the table that, because you're pushing into the table will push right back up. So those are the 3 forces. They're all vertical. So the normal force, the force applied from you pushing, the force of gravity. Okay, let's start solving this out. So where are we going to start? We got to look at the net force. So we're going to look at the net force in the vertical direction. I'm going to start it up here. So we're going to look at net force in the y for the vertical equal to ma, Newton's second law, just in the vertical direction. Remember the y is because it's vertical. So we're going to write out the net force side. We're going to write out all the forces that we know are present here. So we're going to tally them all up. So we have the normal force. It's going up. Then we're going to add the applied force. That's going to be a negative because it's down. And then we're going to have the force of gravity, also negative because it's down. And then it's still going to be equal to ma. So right here, it's probably a good idea. We don't know the force of gravity. We don't know the weight exactly. But what we do know is we do know the mass. And we do know little g on Earth, right? We do know little g on Earth, and we'd assume this is on Earth. It is 9.8 meters per second squared. Again, remember it's positive because it's just the magnitude. So remember that the force of gravity from the last unit is m times little g. Little g, the magnitude of acceleration due to gravity. So we're actually going to plug that information in. So we're going to simplify it a little bit. We'll get the normal force minus the applied force minus mg equal to ma. So again, I just basically took the force of gravity and I plugged it in, or basically the formula for force of gravity, and I plugged it in. So now we have m and g, and we know both of those things, m and g. So now all that's really left is plug in. We just got to be careful about everything. So we're going to, Fn we're looking for, we don't know that yet. So we get Fn minus 8 minus the mass, right, 0.100 kilograms times the acceleration due to gravity, 9.8 because it's on Earth, times the mass over here. In the acceleration, we actually know the acceleration is going to be 0 meters per second squared because it's not moving. If something's sitting on the table, we're assuming that the table's holding up, so it's actually, we're not going to have any acceleration because it's not moving. If it's not moving, there's no change in velocity, there can't be an acceleration. So the acceleration is actually going to be 0 here. So it makes our lives a little bit easier. So if we simplify this, right, again, this being 0, we're going to simplify it, move it around a bit. We're going to get Fn is equal to 8 plus 0.1 kilograms times 9.8. And then we do that out. We're just going to do that little bit of math out, not bad. So we get the normal normal force is equal to 8.98 newtons. So that is the normal force. So again, looks like a lot, but if we break it down, it's not too bad. So again, that's a nice example problem. Again, make sure you have the problem written down, right? Make sure you have notes annotated, and that is it for now.